Have your notes. Let's dive in. All right, section 4.1. Yes? Oh, yes, I would broadcast gladly. Good? Okay, excellent. So, we're not talking about higher order differential equations, but specifically, we're going to be talking about linear. We're going to focus only on the linear case for now. And when I say linear and higher order, this means second, third, fourth, etc. in terms of derivatives. So this this initial value problem that I have written down here, labeled as equation 1, is an nth order initial value problem, but it is linear. And you can recognize that it's linear by identifying the structure. So it's linear in this yellow variable. It's linear with respect to the y's, right? So that's like your variable. This is like x1, x2, x3. You know, when we were in linear algebra and we had an equation that we called linear, we had a coefficient times a variable plus a coefficient times a variable all the way through. No higher powers, no two variables were multiplied together. It's all linear. So we've covered that before in here. And then your coefficients are these guys out front. So this guy, this guy, this guy, this guy. And then you've got the right-hand side also. But those now are not constant in general, but they may depend on x. So these can be very complicated functions, or they could just be numbers. Any of those things, you still have a linear structure to the differential equation. And then, as we've indicated in the past, all of these down here, the number of the initial conditions that you have will match the order of your equation in initial conditions. Okay. Now, as we go through this chapter, what we're going to end up doing is we're going to talk a lot about how to find these solutions. We'll start simple. We'll start with constant coefficients, and then we'll build up from there and show that we can come up with a solution to just about any of these, at least under I should say, we can find the solution to all of them, but we don't like the solution to all of them because we may have to resort to power series, which means we don't have a nice closed form, finite expression that would be the solution, but I can still come up with the solution. We'll touch on power series at the very end of this. But for now, we're going to spend this section 4.1 going through talking about basically terminology. We're not going to talk about solution techniques until 4.2. The linear nth order ODE of the form in equation 1 is called homogeneous whenever the right-hand side is 0. We got to break this down into basically two problems. We're going to solve homogeneous and we're going to solve non-homogeneous linear higher order differential equations. I've got an E there. So if the right-hand side is 0, we call it homogeneous. If the right-hand side is non-zero, we call it non-homogeneous. So in order to solve a non-homogeneous equation, we actually have to always be able to first solve the associated homogeneous equation. Okay, notice again, the right-hand side is 0. So if I gave you a general nth order problem and the right-hand side was non-zero, actually the first thing you're going to do is change the right-hand side to 0, solve it, and then come back and we'll talk about how to solve the other part. I want to introduce to you some notation you've actually seen before, but it's actually going to be something we use both in this section and in this chapter and later chapters. It's the differential operator. This is as good a time as any to refresh your memory of what the differential operator means. Instead of using dy dx, I will very often use this capital dy to indicate the derivative of a function, an ordinary derivative of a function y. So this, just a capital D from now on, means d dx. And actually, instead of writing y double prime, or instead of writing dy squared, or sorry, d squared y over dx squared, I may just write d squared. D cubed, right? D to the third actually means third derivative, so that's d3 of y dx cubed. This is dn dx n. Actually, I don't need the y's in there because I don't have the y's in there. On the left-hand side. Okay. One of the main reasons we do that is because it helps us recognize what would essentially be a quadratic operator when we rewrite this in differential operator notation. So the second derivative is the same thing as d squared y. Then we'd have plus 3. The first derivative is dy, and then minus 4y equals 0. Okay? So these two things are equivalent, right? But I can also think of this as a single operator being applied to y. It essentially looks like I'm factoring out the y, but keep in mind, in this notation, the operation between the d and the y is not multiplication, so it's technically not factoring. What it is it's the operation of taking the derivative. So I'm using this side-by-side notation to mean that d squared is to take the derivative of y twice. But I'm writing it as I would write the square of a number, meaning I'm raising it to the second power, but all it really means is repeated differentiation. It doesn't mean repeated multiplication. So I would write this as d squared plus 3d minus 4 applied to y equals 0. That's also equivalent now. So this is essentially a new differential operator. And operator theory is a very interesting field in mathematics because you start thinking of the things you do to functions instead of the things you do to numbers. Algebra is a lot about what you do to numerical values and summarizing those with algebraic notation. So when I say take a number, square it, add 3 to it, and then divide by 7. You write that as an algebraic expression using variables as placeholders. So algebra becomes the way to summarize operations on numbers. Well, then operator theory can do the same thing. You can take a function as your starting place and say, take the second derivative of that function, and then multiply the first derivative by 3 and add it to the first thing, and then subtract 4 times the original function and tell me what you get. That is an operation on y, on the function. And in this case, now we think of differential equations as the solutions to operator algebra, operator equations. Okay? That is, we want to find the y so that this differential operator turns it to 0. Okay? We want to find, in fact, all the functions that this differential operator destroys. Actually, there's a very good mathematical name for this. Whenever you find an operator, actually, for an operator, whenever you find the set that all of those things go to 0, you're basically finding the annihilator. That operator is the annihilator of that set. In fact, later on in this section, we're going to use something called the annihilator method. Just sounds awesome. We're going to be annihilators by the end of chapter 4. There's also a more boring word. It's also the null space of that operator, which you will have also recognized that term before, but I like annihilator a whole lot better. Okay, so the nth order differential operator is one that can be written in this particular form. Notice basically all I've done is the same idea of what I did on example at the bottom of page 1, but I did it up here to equation number 2. I replaced all the y's here with all the, derivatives of y with now capital D to the ny, capital D to the n minus 1y, and then factor out the y And then this right here, this L applied to y, is exactly the same thing as a n of x d n plus a n minus 1 of x d n minus 1 plus dot 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 plus a 1 of x d plus a 0 of x. That's L applied to y. Okay? So notice what this actually tells me is equation 2 is equivalent to Ly equals G. So if L is an nth order differential operator, then we can rewrite the whole nth order linear differential equation, number 2, as Ly equals G.
What is that?
Equation
Equation 2?
2 I've got up here. See labeled.
I'm just asking because it's hard to tell what that is on the equation when you wrote it down.
Oh, yes. That's sloppiness of the tablet. Surely it's not in my handwriting. We describe an operator as being linear if it has the property that when you take L applied to a linear combination of two functions, you get a linear combination of L applied to those two functions. Sounds like I said the same thing twice, but I didn't. I said something very different. It's linear if L applied to a linear combination of two functions is the linear combination of L applied to those two functions. Namely, alpha times L of f of x plus beta times L of g of x. Essentially, an operator, L, it doesn't have to be a differential operator. Any kind of operator on a function is said to be linear if it has this property. Okay? It's actually two properties in one. It says L of alpha times f is alpha L of f, and L of f plus g is L of f plus L of g. These two properties together is equivalent to this one property by itself. Now you recognize those properties probably in the context of calculus because this is something you can do with a derivative, right? The derivative of a constant times a function is a constant times the derivative of the function, right? You can pull the constant outside. And you can also take the derivative of a sum as the sum of the derivative, which means that a first derivative, just by itself, the derivative operator, is linear. Okay? Another operator that's linear is the integral. The Riemann integral of a function is linear because the integral of a sum is the sum of the integrals. And you can always pull constants outside the integrals. Okay? But there are other functions of functions that aren't. I mean, just think of plugging a function inside of a trig function. Right? Sine of f of x. If you have an alpha inside, you can't just pull the alpha outside of a sine. Right? So some things that you put inside of other functions, you can't pull constants in and out. But derivatives you can, integrals you can, trig functions as operators you can't. And there are other types, well, I don't want to get too deep. Consider the operator L of y equals 2y. If I ask you to show that that operator is linear, this is a kind of textbook, easy proof, straight out of proofs class. If I told you that the linear operator L is to multiply a function by 2. Okay, so this is a particular type of operator, well, where if I say apply L to a function, that means just multiply the function by 2. That's what L is. That's the operator that it is. To show that it's linear, we need to show that this is equal to this. Okay? So we need to show that L of alpha f plus beta g, when L is to multiply the function by 2, is the same thing as alpha L of f plus beta L of g. So proof. Start with the left-hand side of the definition and show that it equals the right-hand side.
Prove it underneath. Let's just prove it already.
Oh, I already have space to do that. Pay attention to my notes. No, this is two different proofs. I want to prove this linear operator.
Okay.
Down here I'm going to prove this one. You threw me off for a second. So let's start with this one, and we'll prove the thing about the differential operator in just a second. All right, so proof. Put that back in there. All right, what is L of alpha f plus beta times g? I'm going to be lazy and leave off the of x's part because it's implied. All right, so in this context, that means to take whatever's inside, right? So if you plug in a y, you get 2y. So now I'm going to take all of this here and just multiply it by 2. That's what that operator now means. 2 times alpha f plus beta g. That's by definition of the linear operator. And now that operation in here is just multiplication, so I know that I can distribute the 2. So I have 2 alpha f plus 2 beta g. Because multiplication distributes across addition, even function addition. What I'm trying to get to is alpha times L of f plus beta times L of g. Well, pull the alpha out of the first one and write it as 2f. Plus, take the beta out of that one, 2g. That's because of associativity and commutativity, actually both, of multiplication. And then 2 times f is the same thing as L of f, plus 2g is the same thing as L of g. Back from the definition. Proved. L of alpha f plus beta g is alpha L of f plus beta L of g. So that particular operator is linear. And just for the record, that's what linear always means in mathematics. Okay? That thing you learned back in algebra that said linear was if it graphs as a line, that was a lie. That's not what makes something linear. Somebody tried to fool you with that. They just kept it simple because in that context, yes, linear functions graph as a line, but we have generalized the concept of linear to mean so much more. It's where we got the name, of course, line, or linear, right? But now linear has been expanded to mean this. Any operator is linear because of this definition. You go in any higher level mathematics, this is the definition of linear right here. You'll see that over and over and over again. Okay, so the question is the differential operator linear? In other words, let L of y be dy. By the same argument, can we prove that dy is linear? So, consider d of alpha times a function f plus beta times a function g. In fact, not even consider what we want to show. I always like to do this at the beginning of my proofs. Those that had me for linear algebra have seen that before. If you've not, from now on, when I write WTS, I haven't proven anything. It's my game plan. It's my strategy. It's my goal. Okay? Wish to show. I want to show that that is equal to alpha df plus beta dg. The worst beta ever. There we go. If I can show that, then I will have shown that it is linear. Now, I'm skipping the step of writing out the reasons, but you need to make sure you understand the rationale of how I go from each line up here, say, to the next line. That's what proofs are all about, is being able to understand the rationale. So let's start with the left-hand side, d alpha f plus d beta g. What is that equal to?
D alpha f plus d bg.
Why?
Distribution function.
No. I'm not multiplying, so I'm not distributing. There's another reason.
So we just proved it for it.
Nope, we didn't prove it for the differential operator. We proved it for 2y. Because the derivative of a sum is the sum of the derivatives. That is proven in Calculus 1 from the definition of the derivative. When you define the derivative as this limit of the difference quotient, one of the very first things you do is start looking at properties of derivatives, and you prove, mathematically, you prove a theorem that says the derivative of a sum is the sum of the derivatives. So I'm using that, okay? This is called the sum rule for derivatives. Said I wasn't going to write it out, but now I did anyways. Now what can we do on the next line? Problems? You sure? Not that you want to share with the whole class. We'll share with Cassidy and she'll console you. What can I do? Pointing at it. Okay, by what rule?
Derivative of a constant.
Times a function is
The same as
the constant times the derivative of the function. Yeah. It's a scalar multiple rule for derivatives. But don't call it the constant rule, because constant rule is the derivative of a constant is 0. But it's the scalar multiple of a function, or a constant times a function. Same thing here. B beta times d of g, which is, by the way, what we were trying to prove. So put you a little box, revel in the glory of the Halmos. Do you know that has a name? I don't know if I ever taught you the name of this. The little box has a name.
Really?
It's not the little box. I mean, the box that we put at the end of the proof, the goal of every mathematics student is to get to the box, to get to its name. It actually has a mathematical name after a dude that basically conventionalized this. His name is Paul Halmos, Halmos. He only passed away like a few years ago, but he's a popularizer of modern mathematical proof notation. So the little box here, named the Halmos, we give him honor for that. So that goal, we have reached the Halmos QED.
Everyone has their own little box.
Do what?
Everyone makes their own little box kind of.
They can vary from one person to the next. I know that whenever you see it in a math journal, usually it's a closed-end box. Actually, I think when you typeset a math paper, which you're going to have to learn how to write a math paper in this class.
In this class?
In this class, yes. Because you have to write up your group project report. You're writing a math paper. There's a language used to typeset mathematics that's so much prettier and better than Word. Nobody actually writes in Word. Whenever you're a mathematician, you write in a language called LaTeX. And don't let Dr. Hahn tell you otherwise. That's how you pronounce it. LaTeX, not latex. He doesn't say that, but he says LaTeX. Nobody says LaTeX. LaTeX. Ask the mathematicians, not the statisticians. Point being, that LaTeX is this typesetting language, and I think the symbol for that is you put a backslash. It's what you do to write up a math paper that you're going to submit to a journal is you actually write it all in a text editor. So you're like in Notepad or WordPad or just text, ASCII text, and so you typeset all of your mathematics by text commands that tell it. Once you run it through a compiler, it turns it into a nice, pretty document. So, like if I wanted to get pretty alphas and Ds and Fs and parentheses that are bigger than other parentheses, I have to learn a language on how to typeset all of that. And whenever I want to put that little box, I put backslash Homos. It shows up in here. I have no idea why I went through so much detail on that little fact right there.
Thanks.
Now you know. I guess I had to throw in a dig at Dr. Hahn somewhere. Try to get that in every class. All right. Okay, so that's linear operator theory, which is relevant at different points within this course, and in particular in this chapter. I'm now changing gears, so this big long line here means store that information. We will use it later, but it's not related necessarily to this next one. But I want you to store this information now, too. There's something with linear differential operators or linear nth order differential equations that is very helpful, something called the superposition principle. And it actually has to do with the fact that these things are homogeneous. First thing I want you to do is I want you to just take a look at this differential equation, back yourself up to section 1.1, 1.2, when we first started talking about differential equations and initial value problems. Let's just verify that if I give you this solution right here, that is in fact the solution to that differential equation. Okay? So plug it in. Y1 prime I need to know is 2x. Y1 double prime is 2. Y triple prime is 0. Okay? So plug that into this equation and make sure that it's in fact a solution. You get x cubed times 0 minus 2x times 2 plus 4 times x squared. Nope, that's 2x right there. Sorry.
Did we need to write anything in the ODE and IVP because we were using a differential operator? Is that
No, because I actually wrote it accidentally up here.
okay.
That was what was supposed to go there. This was up here with this guy. I was watching one of my videos the other day and realized I get a little arrow happy. I do too many arrows. Draw arrows everywhere. Do you like my arrows? Should I cut back on the number of arrows?
No, it's great. Keep it.
It's gotten a little bit better because I've added that thing so that I have my actual pointer on the screen. Before, all I had was a little red dot and you couldn't see where I was trying to point, but now I can do this and not draw on the screen. By the way, do you like the pointer better, or do you like maybe a pencil? What do you think?
At least really.
You like the pencil? Or how about the red dot? Just nice.
I'm really
Big.
happy with the thing done.
What do you think? No?
No, I don't like that. Definitely the pencil.
She definitely just used the banana.
I wish there was a banana. Actually, I never thought I'd say that in the middle of my differential equations class.
You can probably get
Equals 0, check. Okay. Let's also check y2, which is x squared log of x, is also a solution. I'm not telling you yet how to find these. We will eventually have some strategies to solve for these. This turns out to be what's called a Cauchy-Euler differential equation, which we're not going to cover in class, but I'm going to give you a video to watch outside of class to learn how to solve Cauchy-Euler ones. They're actually pretty much the same technique with a different starting guess. But for now, let's just plug it in and make sure. So first of all, y2 prime. It's a little bit more work because we've got a product of two functions. Is that what you got? First times the derivative of the second, x squared times the derivative log of x What's the derivative of log of x? 1 over x. So x squared times 1 over x is x. And then the derivative of the first times the second would be 2x times natural log of x. So this equals, derivative of that's 1, plus now, product rule on this first times the derivative of the second is going to be 2x times 1 over x, which is just going to be 2, plus the second times the derivative of the first, which is 2 log of x, which is actually 3 plus 2 log of x. And then y2 triple prime is 0 plus 2 over x, so just 2 over x. All right, plug all that in. So x cubed times 2 over x minus 2x times y prime, which was x, plus 2x log of x, plus 4 times x squared natural log of x. That gives me a 2x squared minus 2x squared minus 4x squared log of x plus 4x squared log of x, which is 0. Okay. So I verified y1 and y2 are both solutions. So essentially what I can say now is that x cubed y1, third derivative, minus 2x y1 prime plus 4y1 is 0, and x cubed y2, third derivative, minus 2x y1, sorry, y2 prime, plus 4y2 is also equal to 0. Have y'all seen this symbol before?
No, it's an and.
And, yeah. The fewer words I have to write on a proof, the better. And I got to keep exposing you to it so that you're slowly learning the language that we speak or write in mathematics. So, and wedge means that. By the way, it's called a wedge in LaTeX. That's / wedge.
Much less tedious than just writing and.
Well, you make a good point. If I'm writing by hand, it's less tedious, but then I have to go write up the paper and publish it, and you're right, that is a whole lot more tedious. But we start speaking, I mean, you think in LaTeX. What'd you say?
Like on number 6 on the keyboard, why don't we just use that for
It's a little smaller,
They carry it.
and I actually use that for superscript, so to get something to go up into an exponent, you use that. All right, now here's the real crux of this. I now claim that you can now write down a general solution to this by any combination of those two solutions. That is, any constant C1 times the Y1 I gave you, plus any constant times Y2 is also a solution to the differential equation. I want to prove that. Okay, so this is my new Y. I want to plug this in here to this differential equation and prove that I still get 0. And basically I'll use these two facts right there. Okay, so first of all, y prime would be C1 y1 prime plus C2 y2 prime. Y double prime would be C1 y1 double prime plus C2 y2 double prime. and y triple prime would also be c1 y1 triple prime plus c2 y2 triple prime. That's just from the linearity of the differential operator. So now plug into the DE, the differential equation. And here's what I get. X cubed times C1 Y1 triple prime plus C2 Y2 triple prime minus 2x times C1 Y1 prime plus C2 Y2 prime plus 4 times C1 Y1 plus C2 Y2. All I did was take this new y and plug it in up here to the original equation up there. Okay? See it? Everywhere there's a y triple prime, I put this. Where there was a y prime, I put this. And where there was a y, I put the original y. Okay. Now I'm going to do algebra. Take the x cubed, distribute it, 2x, distribute it, and the 4 and distribute it. Then I'm going to put all the y1s together and all the y2s together, and then I'm going to factor out all the c's. Again, I'm going to put, once I've distributed, I'm going to put this, and this term together. And then I'm going to put this term together. And then I'm going to factor out the c's. So distribute, collect, factor. And here's what I get. All the yellow ones have a C1 in it. So I pull it out of all of them. And I'm left with x cubed y1 triple prime, right? X cubed times this term, pull out the C1, I got x cubed y1 triple prime. Minus, move the 2x in, I got minus 2x, pull the C1 out, y1 prime, plus 4y1. Now I do the same thing, take the x cubed, put it inside here, but pull the C2 out. And you've got x cubed y2 triple prime minus 2x y2 prime plus 4y2. And what do you recognize? Where do you see that? It's right up there.
Oh, yeah, it is.
So all that's equal to, that's not what I wanted.
0.
That's all 0. And then this guy right here. Oh, that was a
Wow,
good
that's
choice. Let's try that again. How about this dude? This one is this one. Actually, what I really need is more arrows. Right? So C1 times 0 plus C2 times 0, which equals 0, which means it's a solution, right? So y equals C1 y1 plus C2 y2 is also a solution. That's great news. Tells you that when you have a differential equation like this one, and you have two solutions, then any linear combination of those two solutions is also a solution. But there's a very key important property that it has that makes this work, and it's the zeros. Right? It's the zeros here, here, that turn these into zeros here, that make this a zero here. The key is it has to be homogeneous. The superposition principle is going to say any two solutions, you take a linear combination, that's also a solution as long as you start with a homogeneous equation. Okay? So, superposition principle, homogeneous equations. If y1, y2 through yk are solutions of equation 2, remember equation 2 is the main differential equation that we're talking about, the linear nth order, over some interval I, then any linear combination is also a solution as, by the way, equation 2 has a 0. Notice it's not equation 1, which has a g. Equation 2 has a 0. It's the homogeneous one. Is homogeneous. Proof skipped. I don't want to go through it. I'm running behind on time. Omit for time sake. Corollary to that, if you have a single solution, then any scalar multiple of a solution is also a solution. And the trivial solution is the solution to any homogeneous equation. Just let C be 0. And thus y equals 0. The constant function y equals 0 is a solution to the homogeneous equation. Okay? All right. So now we need to come back and talk about something that those of you that have had linear algebra have seen before, but is important in this context, because what we really want to do is we want to come up with the most general set of solutions to any given equation. The way that we do that is we find all these y's that solve it and set the solution equal to c1y1 plus c2y2 and so on. Essentially what that will mean is that if I have an nth order equation, I need n y's, and I'll put a c in front of each one of those y's. But those y's that I've chosen have to have the property of being independent from each other. Meaning that you can't write one in terms of the others. Right? I could say one of the y's was x, I think up here. If y1 was x squared, I wouldn't want to say y2 is maybe 3x squared. Because this y2 is not really any different than this y1, other than it's a constant multiple of it. Right? Whereas this one is a completely different function. And what do I mean by completely different? Well, that's this terminology down here of linear dependence and independence. Okay? So here's the definition. A set of functions, f1 through fn, are said to be dependent if there is some set of constants that are not all zeros, so that you can combine those functions together and get 0. Get identically 0. Okay? In other words, you know the f1, the f2, all the way through the fn. If this has a non-trivial solution, then they are dependent. Okay? So if there is a non-trivial solution to 3, then we say they're dependent. On the other hand, if equation 3 has only the trivial solution, in other words, they are all zeros, then the functions are called linearly independent. And again, if you've had linear algebra, you remember dependent, bad, independent, good. Okay, so here's an example we can do what I call the hard way of actually plugging into this equation and seeing if there is a solution to it. So let's ask if cosine squared, sine squared, secant squared, and tangent squared are dependent or independent. So one way to check that is just by virtue of the definition. That is, take C1 times F1 plus C2 F2 plus C3 F3 plus C4 F4 equals 0, and solve for C1 through C4. Now again, you recognize you have not enough information to solve uniquely. That is, you don't have 4 equations with 4 unknowns. You have 1 equation with 4 unknowns. And by the way, I should be careful. This equal sign actually has 3 bars, not 2. You know the difference between a 2 and a 3? Why am I adding an extra bar to my equal sign?
Absolutely equal. Equivalent.
It's identically equal is the word we use.
Is there-
Carries the same meaning as universally, but what does it actually mean?
When you say identically equal, it just sounds redundant to me as well.
Okay, well, let me write an equation over here. If I said x squared plus 2x plus 3 equals 0, what does that typically mean to you?
Oh, we have to find an x.
You find an x that makes that 0, so you can solve that. That's what's called a conditional equation. It's true as a condition of x. But if I wrote down x squared plus 2x plus 3 is identically equal to 0, which is, by the way, not true, what that means is that this thing is 0 for all x. Okay? Maybe a better example would be sine squared of x plus cosine squared of x is what? Equals 1. Now we typically write it this way, but what we really mean is it's identically 1. It doesn't matter what x is, it's always 1. That's an identity, not a conditional equation. So what I'm saying up here is that I want, notice how on the left-hand side I actually have the variable x in there, right? I want the left-hand side to be equal to 0 no matter what x is equal to. So I'm going to try to find a C1, C2, C3, and C4 that makes that identically equal to 0. Now obviously, if I plug in cosine squared of x here, plus C2 sine squared of x, plus C3 secant squared of x, plus C4 tangent squared of x, I know a solution just by looking at it. The 0 solution is always a solution, but the question is there another solution to that? Can I find other C's that would make that 0 identically? And I've kind of given you a hint already by thinking in terms of trig identities. Let's say I let C1 equal 1 and C2 equal 1. Why am I choosing those? Well, I'm choosing those because I know sine squared plus cosine squared is going to give me the number 1, right? But there's also an identity that involves secant squared and tangent squared. You remember it?
1 over.
Sine squared plus cosine squared of x equals 1. There's the cofunction relations of secant is 1 over cosine and tangent is 1 over cotangent, but I'm actually thinking back in terms of this guy. Remember that there's another Pythagorean identity that has to do with secants and tangents?
Oh, secant squared x is equal to 1 minus 2 squared x. Or
I think that's right. Yes. If I divide this through by cosine squared, I get tangent squared of x plus 1 equals secant squared of x.
Yeah, something like that.
Right, so I just divide that through by cosine squared and realize that sine over cosine is tangent, 1 over cosine is secant. And that gives me this trig identity. Actually, I never remembered this off the top of my head. So whenever Jeremiah started shouting at me, I didn't know if he was right or wrong. I had to do it in my head. I have to remember this guy and then I remember that I divide through by cosine squared. I can also get the other one by dividing through by sine squared. I can get that 1 plus cotangent squared is cosecant squared, right? But here's the thing. If I put in ones here, I get cosine squared of x plus sine squared of x, which, by the way, is going to give me 1, right? Is there a way to combine secant squared and tangent squared to get maybe a negative 1? Like, look at this guy. If I moved him over here and him over here,
Tangent squared minus secant squared.
tangent squared minus secant squared of x gives me negative 1. So if I use C3 as negative 1 and C4 is 1, then I'll get plus a negative secant squared of x plus tangent squared of x, which, by the way, is, according to this, negative 1. Always, for all x, which gives me 0. So this right here represents a non-trivial solution, which means they are dependent. Now, I chose this problem intentionally because I know those relationships between sine squared, cosine squared, secant squared, and tangent squared. But in general, what if I gave you x squared and x squared log of x? I don't have identities to work with that way. So this will only work in a very special set of cases where I can try to figure out a C1, C2, C3, C4 that work. So there has to be an easier way. There is what's called a Wronskian method. Now, I think that I did not cover that in differential equation or in linear algebra. Have you ever heard the word Wronskian?
Sounds like a Star Trek thing.
It's an awesome, yeah, it's not the Klingon word for anything. Maybe it's Klingon for linearly independent. Probably not. I mean, if they have the technology they have to build cloaked birds of prey, then they have to be able to done the mathematics of linear algebra to get that far in with space exploration. So I'm assuming they have Klingon for these terminology. I don't know why I went down that road. Let's, I think because I changed textbooks, we didn't talk much about this. We talked about linear independence and dependence a lot in linear algebra, and we did things like the determinant to check whether or not a set of vectors was dependent or independent. We also did, well, that was the main way to do it, was to check the determinant. You put them in columns and make a square, and then you calculate the determinant. If the determinant was 0, they were dependent. If it was non-zero, then it was independent. That was how the determinant worked. Well, the Wronskian is a technique that uses the determinant to determine whether or not a set of functions is dependent or independent. So you got to know how to find the determinant to be able to do this. I'm going to go through it relatively quickly, but you'll only have to do maybe 2 by 2s or 3 by 3s in this class. We won't have to do big cofactor expansions for 4 by 4s and higher for those of you that haven't had that yet. But here's how the Wronskian works. The Wronskian is a formula whose inputs are a set of n functions. Okay? So the Wronskian W is a function applied to a group of functions. And what you do is you take the determinant of this matrix. Now, the first row of the matrix, you just put the functions on the first row. So like on our previous example, we would put cosine squared, sine squared, secant squared, tangent squared. That's the first row of your matrix. Okay? On the second row, you put the first derivatives. Second row is the first derivative. And then notice how it progresses all the way down to the nth row is the n minus 1 derivative. Actually, I technically think that's the n minus first derivative. We like adding those little words. I like words like nth and n minus first derivative. But do you see how each row you just take the derivative of that particular function? So your first column is your first function. So the function, first derivative, second derivative, all the way down to the nth derivative, n minus first derivative. Now the reason we only go to n minus 1 is to make this square. So you have an n by n matrix, right? Because you start with the function, which is essentially the 0th derivative, then the first all the way up to n minus 1. So since you start with 0, you end with n minus 1 to get n in that column, in rows. And then the determinant means you're going to actually take the determinant. That's the formula that we learned in linear algebra. For 2 by 2s, A, B, C, D. What's the determinant of a 2 by 2? What's the shortcut? AD minus BC. Okay, that comes into play, and again, determining whether or not these vectors AC and BD are linearly dependent or independent. It can also be used in solving matrices. You can use Cramer's rule. You know how much I love Cramer's rule?
You named your dog.
I had named my dog Kramer. He was 17 years old last year when we had to put him down. It's terrible.
That's a very long time though.
He was a very old dog.
What breed was he?
He was a dachshund.
Those dogs typically live that long?
Their average age is about 14 or 15, so he was a little longer. Okay, so the determinant for 3 by 3s, there's also a shortcut for. Do you remember it? Four diagonals.
And you put the 2 on the right side.
Yeah, or you do this.
Yeah, we just get good ones. Just for
Those are all plus, and then the back diagonals. And these arrows just mean multiply. You subtract all of those. 4 diagonals minus back diagonals. 4 by 4 and higher, there is no shortcut. You have to do cofactor. That's where you either expand along a row or a column, and you start marking out rows and columns, all that stuff. You don't have to do that in here, I don't think. I may give you one just to see how well you remember it. We'll see. All right, now here's the question. Can I prove these things are linearly independent and dependent? Well, it's this theorem right here that gives you the ability to do that. Okay, so we calculate the Wronskian, and the solution is, the functions are linearly independent if the Wronskian is non-zero on an entire interval of x's. So if you want to say they're independent on a given interval, then as long as the Wronskian is never 0 on that interval, then they're independent on that interval. Now, the Wronskian, by the way, is going to be a function. It's a single function that you get out of it. Because remember with determinants of a matrix gave you a number. Now, all of these things in here have x's in them, so you're going to get just a single function of x as a result. And so as long as that function is never 0, if it's never 0 at all, then they're independent on the entire real line. If there's an interval on which they're never 0, then they're independent just on that interval. But you can at least say anywhere they're non-zero, that set of functions is linearly independent on that interval, which is what we want. All right, so let's consider these two functions and decide whether or not they are independent. So first of all, let's do the Wronskian. We have two functions, so the Wronskian is going to be a 2 by 2 determinant. On the first row of the matrices, I put the functions themselves. X squared and x squared log of x. By the way, it's named after a dude. His name was Wronski. I think he was German.
I'm still Russian.
You might be right. He might be Russian. That does sound more Russian than German. Wronski. The second row is going to be the first derivative of those functions. So directly beneath the x squared, put 2x. And then beneath the x squared log of x, you're going to put the derivative of that, which we learned was x plus 2x natural log of x. Okay? So what is that determinant then?
X squared times x plus 2x ln x. Natural log, I just do
Did you just alone?
minus x squared, natural log of x times 2x.
Oh god.
There is no ln function.
It's ln.
X cubed plus 2x cubed natural log of x minus 2x cubed natural log of x. Okay, so that's the Wronskian. Now, what can we then say about whether or not these are linearly dependent or independent?
Well, it's not true, though.
Can this ever be 0?
Yes.
Yes, if x is 0, right? So it would be dependent on any interval containing 0. It would be independent on any interval not containing 0. Okay? So this is 0 for x equals 0, which means this set, x squared and x squared natural log of x, are independent on any interval I not containing 0. That's all we can say.
Wait.
They are not independent everywhere on the whole real line. We can only say, for example, if for some reason I wanted to describe the solution to the differential equation over the interval from 0 up to some number r, they would be independent on that interval. But they would not be independent, meaning they'd be dependent on an interval that contains 0. Okay? That's what the theorem about using the Wronskian for finding whether or not functions are independent. Okay. Stop there. I'm done. We will now talk about how we actually come up with the solutions using what are called fundamental sets of solutions, homogeneous and non-homogeneous, and then we will dive into actually finding solutions. The good news is 4.2 is very short and easy to do. It's 4.3 that gets interesting. No, we skipped 4.2. 4.3 is very short. 4.4 and 4.5 are the challenging ones. The homework for this section is not yet posted. It will be up later, but it won't be due until Thursday. No. Next Tuesday, I mean.